and good morning from my side. I will start the presentation and hand over to Mauro as soon as we are through the introduction part. Firstly, in the title, you've seen the mention of this soft open point. I guess it is useful that I quickly summarize what the soft open point is supposed to be. In a nutshell, it is a device that is there without being there. I explain. Suppose you have a ring topology, as in medium voltage, which is operated as an open ring, or you have low voltage network, which is a radial network with neighboring branches. These branches cannot be connected and should not be connected for protection reasons, but you may want to connect neighboring branches in order to better share load or in order to do a bit of voltage regulation. And the soft open point is therefore a power electronic device that is able to fulfill both requirements, to be closed in normal operation and to be open in fault case. This device will help the network to absorb more renewables, and therefore, if it does its job, well, it will reduce the loading of branches and of transformers. Maybe it will also reduce the voltage variation over time, and it should contribute to lowering network losses, which, well, indirectly contributes to increasing the renewable energy sources hosting capacity. So this is how we measure the performance of such a device. Now we have this, let's say, brilliant idea. So 3 questions arose to us. Firstly, where would we like to put this device? Secondly, which size of device would we be going for? And thirdly, how would we be controlling that device before starting a practical test? First question, where to place the soft open point? Well, the rough area was given by the REAL project, so it was selected to be in Chapelle-sur-Moudon, which is served by 2 low voltage substations. There is a pink one and a blue one, let's say. Those 2 have multiple, let's say, interface points. You can see they are numbered here along. And we first of all, let's say, had a look where could we put this soft open point, made a candidate list, set up a little ranking system, and you can see here the one which gives an advantage compared to the current situation is location number 1. So as a consequence, we selected this location number 1 for further planning. Secondly, which size of a soft open point would be useful to our case? We first of all had a look at how much PV can we add to that system. If there is no soft open point, the answer was 80-ish kilowatt of additional production to the left and to the right of the soft open point. And if we selected to insert a soft open point into that network for different sizes, as you can see here, we would have an increase of the hosting capacity. Sorry for that. You can also see that there is a flattening of the curve here. So the larger soft open point you put, the more PV you can put into the network, but the effect saturates. So the most attractive to us was to add a 50 kVA soft open point, which would allow to add 3 times as much PV into the network. Third question is, how are we going to control that soft open point? Here, there is a lot of possible schemes. The requirement posed to us was relatively stringent. It has to be independent of other systems in a fallback mode, and it had to be simple. So we based our control in a restricted mode by just measuring currents and voltages at the transformer stations and the soft open point location. We made a few candidate formulation of, let's say, set point definition algorithm, and we compared those to each other. You can see here a performance score where a lower score is in fact a better mark. And to the left side, you have the initial state. So without doing anything, then we could, in the red bar, add just a cable, which would decrease the performance because there is more circulation currents, and we could do an OPF. The advantage of the OPF or the disadvantage is that you have to know everything, and in between are the candidate algorithms. So the best one was a mix between voltage variation and load balancing between the two transformers. Therefore, we selected that and we implemented that into a simple system which only uses radio communication in order to be independent and to ensure the protection. There is a lot of protection functions here which are due to the experimental nature of this device, and we use then a transfer tripping between the distribution substations and the soft open point location, which is based on state-of-the-art, let's say, standards. Of course, then in a future vision, we can envisage to integrate this communication into any available real-time system, which at this point of the grid was not available. There is an integration with the grid eye system, which is implemented to the left and to the right of the soft open point. This integration allows to have additional information in the set points determination algorithm. However, this is not a requirement for the protection to work, and so the system can be seen as being safe. This has all been implemented under previously described pandemic conditions. However, I'm glad to say that the control system is finalized and ready to be integrated into the network. And the next step, of course, is to discuss the actual active part of that system, which is the power electronic converter. And this is where I hand over to Mauro. Mauro, you have control.
Yes, thank you very much, Patrick. I'll try to get the control. Okay, partager. Can you see? Can you see my screen?
I don't think yet.
Okay, let me check again. Okay, is now available to see?
Positive.
Mauro.
Good. Okay, so last thing is to start the diaporama. Okay, so if everything is good, you should see the diapo with the power circuit principle. Okay, as you can see, the power part is made by two inverters in back-to-back configuration. We have a LCL filter on each part of the two grids. We have, of course, the protection that has been developed by Patrick and his teams. And we also have a neutral controller, which I will come back later. The control card is made by two DSP communicating each other, so they are synchronized. We develop all the measurements, current, voltage, etc., and inverter control. And we also make the communication with the PQ reference calculator that has been again provided by the part developed by Patrick. Okay, so a few words about the power circuit control. In the figure, you can see the principle of the control. This is not the actual control. And because we are still publishing, so for the moment it's reserved, but it will be made available to the community with the next report. And but the principle is quite easy. It's control the separate is current control first of all. Even we've developed also the voltage control, so we can work both in voltage follower and in grid forming capability. But in the Chapelle will be installed the current control. And the control is made in DQ coordinates, and actually this control will be modified to take into account that we have an LCL filter. One of the converter is supposed to make also the DC link control, and this is interchangeable. So that means that according to the grids that are available, to the grids condition that are available, we can decide if inverter 1 or inverter 2 is making the DC link control. The reactive power on the two sides, of course, is independent, while the active power, of course, is connected. And I think that's all for the moment. So I just want to come back to the neutral control. This is relatively new. Is the problem of controlling the neutral in a three-phase inverter under unbalanced condition is known, but we developed a new model, and you can see here the short summary of the state space model valid for a small variation that we developed. I think that this is a real novelty, and this will be published again in the next future. And this will be something that is useful for this application and allows the system to work under unbalanced condition, both in voltage source and in current source application. Okay, so going deep inside in the hardware, the power circuit has been designed with HEIG-VD modules. 1200 volt and 200 amps. You can see the LCL filter chosen. Usually the grid filter is a little bit lower than the L filter, but we designed it a little bit differently, and those are the results of our design. On the DC link, we have about 25 of capacity. The DC bus is 800 volts. This voltage is necessary because one of the lessons that we learned from the first prototype that was a 15 kVA prototype we developed inside the SCCER-FURIES. One of the lessons we learned was not to use space vector modulation. Because the space vector modulation is very interesting, but it creates a further harmonics that for this kind of application you can find it. And so you risk to become a further harmonic generator. That means that you need to insert separation, isolation transformer, a 50 Hertz isolation transformer that we didn't want to have. So we decided to remove space vector modulation and accepting that we lost 15% of DC link voltage. But it's not a problem because we have the two converters are connected on the same DC link, so we can decide the DC link that we want to have because it's controlled, and of course we have to accept that we have a little bit higher DC link voltage. On the right, you can see the actual inverter, and it's based on the modules that on each module there are a full arm of the inverter. You can see also the heat sink and the polypropylene capacitor in order to stabilize the voltage on the modules, etc., etc. So all the hardware has been developed by ourselves. So we developed also a voltage and current measurement card. We developed the control card, except we decided to not reinvent the wheel. So we decided to use modules, DSP modules made available by Texas Instruments. And of course, we developed the HEIG-VD driver card. Okay, this is an overall layout of the coupler. You can see on the left, on the right, the protection part, and also the PEQ set point calculator. This has been developed by, again, I repeat, by Patric and his team. And on the central part, you can see the SOP ARC section. A lot of evaluations have been made concerning the ambient situation, because this has to be located. This cupboard has to be located outside, so we have to take into account the summer condition and to evacuate the losses, but also the winter condition. So those two extreme conditions has been considered into development, and okay, that's all. Details will be available in the report. Where we are. we tested the first one of the two inverters. This you can see the static behavior at the full power at 220 volts grid and 72 amps of the phase current. This is the current injected inside the grid. The prototype, okay, we already have tested the second inverter exactly in the same way. So we are now able to transfer active power. Here you can see that just reactive power is controlled. And we are now able to transfer active power between the two inverters. This is a matter of these days. And the on-site installation is foreseen by the end of 2020. This is limited to 39 kVA capacitive reactive power because our emulator Rigatron is rated 50 kVA. Okay, so let me get to the conclusion. The design and the building of the 50 kVA SOP, 2 times 50 kVA SOP prototype are to be finished by the end of this year. The on-site test will start at the beginning of next year. This prototype benefits from, first of all, from system studies, mainly performed at Fribourg, by the design and simulation activities performed here, and last but not least at all, the experience that we made with the first 15 kVA laboratory prototype that has been developed here in the frame of SCCER-FURIES. Of course, aim of the test will be to validate the usefulness of the SOP, of course, as system level. So Mario, I think that I'm finished, and I would like to thank you all for your attention.